So firstly, it's my great pleasure and honor to be invited to join the conference for Jean-Pierre and also to give this talk. And I shall show you a couple of the pictures. Okay, that is the Chern Centennial Conference held by MSRI and our institute together. Actually, Robert and myself spent a lot of time on this one. And Jean-Pierre was very kind to come from very far away and also give a speech here. Later on, also give a lecture on the Chern's life. And everyone appreciated that. And also, at the same time, the second day, our university issued him an honorary professorship. This is the president to issue the budget to him. And the next one is we three talk together. So congratulations for after the 2 years. And also I would like to thank Jean-Pierre for his great contribution to the friendship and collaboration between the French and the Chinese mathematicians. And especially during the time when I was the director of the Chern Institute, Jean-Pierre came and we signed the contract between our two institutes to further the collaboration. And also really I appreciate Jean-Pierre did a lot of things for the Chinese, especially the young mathematicians, encouraged them and give them an opportunity to come to study. So I shall talk about the closed geodesics. Certainly here I believe everyone knows the notation. So it's based upon 3 papers of myself and my former student, Duan. So first, the closed geodesic is that we want looking for a closed curve, and which is locally the shortest. Okay, and thanks to Robert, he already talked about the Fensler structure, so I shall skip that. And we shall use the notation for the iterate. Iterate means that if we have a closed geodesic from, for example, time 0 to 1, then we just run it much faster, m times the original velocity. Then we call that m's iterate. So the problem is that when we count the multiplicity, we need to distinguish whether they are really geometrically distinct or just analytically you get more elements, but they are actually geometrically the same. So this notation means that we consider all the geometrically distinct one. We consider reversible Fensler metric or Riemannian Fensler metric. And the distinct means that just modular S1 action. So this problem certainly has a very old tradition and history. For example, the first result solved by Birkhoff can be traced back to 1917 to 27. He showed that on SD, d-dimensional sphere, for every Riemannian metric, there should be at least one closed geodesic. And Newsternik and Fitt in 1951 showed that just for every compact Riemannian manifold M, and for every Riemannian metric, there should be at least one. And certainly this method goes through to the Fensler case. So we know for every compact manifold, then there should be at least one. Now, in this talk, we consider only the multiplicity. The stability is more complicated, so I shall skip that. And there are some very important results given by the Glomo and Meyer on the multiplicity. For example, they computed the Betti numbers of the loop space, free loop space of the manifold, and they showed that if the Betti number is unbounded, then there should be always infinite many closed geodesics. And then the Sullivan and his co-author showed that this condition, if this is bounded, if and only if the cohomology of the M should have only one generator. But unfortunately, the most important case, the sphere, precisely located in this area. Therefore, if we want to consider this one, then we have to study something very special. So using the result of the Sullivan, start from there. And then later on, in around 1990, Bungart and Franks proved that for S2, for every remaining metric, there should be always infinite many. But both the proofs, since each one proved half of the theorem, both the proofs actually depend on the two-dimensional technique. And those proofs does not go through to the higher dimensional case. And also, certainly, there are many others who worked on this problem and produced lots of results. But still, everyone needs some condition, like pinching condition, like the bumpy condition, generic ones, and so on. So far, this is still unknown. Whether this is true for every compact manifold, remaining manifold. And at the moment, we want to study the case, whether there are always at least two. And here I should mention the result of the Katok. Katok in 1973 construct a family of very spatial Fenster metric on the sphere. And he proved that, for example, by his structure, for the S2, there are precisely 2 close to the geodesics. For S3 and S4, there are precisely 4. And this metric actually just a perturbation of the original standard one by a horizontal perturbation multiplied by alpha. Alpha is an irrational number in between 0 and 1. So this is very important result. Just showed the very important the phenomenon of the Fenster metrics. And after that, the Hofer, Wysotsky, and Sender in 2003 studied actually for S3. But that result can be projected down to the S2. So they showed that for every Fenster metric for S2, provided the Fenster metric is bumpy, that means all the close to the geodesics and their iterates are non-degenerate. And also at every hyperbolic close to the geodesic, all the stable and unstable manifolds should intersect transversally. Under these two conditions, they're able to show that the result, the number should be either 2 or infinite many. This proof is also totally two-dimensional. The reason, there are 2 reasons. One is that they used the open book structure, which so far seems only works for the 3-dimensional case. And another one is they depend on the theorem of the John Franks, which is also a total 2-dimensional phenomenon. And then later on, Bengard and myself proved that for S2, for every Fenster metric, there should be at least 2. And later on, there are some other results for under more conditions. So what we want to prove, actually, the goal is that for every compact manifold, for every Fenster metric, there should exist 2 numbers, the PD and the QD. So the number should locate either in this interval or to be the infinity. And for the Fenster case, for example, for the severe case, we consider this number. The number is precisely the number constructed by Katok. We consider this should be a lower bound. And for the S2 case, this is indeed is true by the result of Katok and also Bengard and myself and the classification of the 2 spheres. So the current goal is that we want to show the total number is at least 2 for every Fenster metric. In the 2009 and 2010, with my former student, Huagui Duan, we are able to show that for S3 and S4, the result is true, at least 2. We used some new method. I shall tell you the method. And recently, actually, in the we announced this theorem in the 2010, and then we finished the last step this year. And we are able to show that whenever the manifold is compact and simply connected, in order to use the result of the Sullivan. So whenever it's simply connected and the dimension is at least 2, we know the total number of the close to the geodesics should be at least 2. And the main difficulty in the proof of such theorem are the following 3. The first thing is that suppose we have one close to the geodesic, we define the energy, like the top 1. Then the critical level of the energy functional actually goes to infinity whenever you do the iterates. Therefore, even you find out infinite many critical levels, that does not mean you have more than one geodesic. So that is the first difficulty. Second difficulty is that from the careful computation of the example of the cutoff in the S2, you can find out that since we have two solutions, one is the equator go forward, another one is go backward. So the one go forward, maybe if you choose this alpha to be very close to 1, then this Morse index maybe occupy a long time. And only the second one only appear very seldomly. So that means all the information of the total number, beta numbers of the loop space in most of the time occupied by the solution. So that means in order to get the information for the second one, you need to run very high iteration. But a priori, you may not know how high you should be. Yeah.
Now, how is the capital M related to the number alpha?
No. I mean the M is the million, 70 million, just the M. Okay. So whenever the alpha is very close to 1, this number can go very big. And then the difficulty 3 is that one can construct, since we use we want to find out the contradiction between the local information and the global information. You can construct some paths so that actually this one can pick up all the such numbers. If this is a degenerate path, can pick up all the beta numbers. So that means the Morse theory is too rough, may not give enough information. The new idea in the proof is that we consider, firstly, certainly we use the variation method. This method actually can also go to higher dimensional case. Second one is that we compute the global information, that means the beta numbers. This for the sphere and the simply connected case already been done by Rademacher in the late 80s and early 90s. The third one is that we are able to show that for every closed geodesic, then we can find out big enough the iteration, tau, so that, and for any given M0 is a certain iterative rate, the time. For any M0, whenever the M is in between 1 and the M0, then Morse index of this iteration can be written into the sum of these two parts and the smaller one. So this is a fixed number. This is a number depends only on the linearized Planck map. Therefore, the total sum of these two actually is a constant for each path. And the fourth step is that suppose we have only one curve. This is always works, no matter how many curves you have. Now suppose we have only one curve, then we are able to show that this curve should satisfy identity, a new identity. So this is the number given here, and this is the number appear there. And these are the beta numbers of the free loop space. And then from this identity, we can derive certain the contradiction by estimates of the Morse index, and the beta numbers take their sum. So
again, this 4, but what's who 4? So what the meaning of the 4 again?
This one. Yes. This means suppose we have only one prime closed geodesic. Then this one is after we chosen this iteration tau. Then this identity always holds. But this kappa, we don't know. This kappa is a non-negative integer. This is the tau's iteration, whose Morse index, plus a constant depends only on the linearized Planck map. And we do not know the kappa. D is a dimension. For example, we consider the sphere in this formula. The D is the dimension of the sphere. And here, this is the beta numbers. So we know this identity. Then from this identity, we can derive certain contradiction. And so the key part is to prove this identity. There we need to prove homological the isomorphism theorem. So that when we go from for example, for the two integers, a and b, in between 0 and m0, if we go from the kappa b, level of the kappa b, energy level, modular energy level of kappa a, this homology, global homology, should be isomorphic to the global homology of the kappa tau. Tau is the number chosen there, plus b modulo kappa tau plus a. But the the dimension of the homology should increase by the number here, by this number. So there are some when you go up to the higher level, then also the dimension will increase. Since this part actually comes from Morse index, in some sense you added this dimensional sphere to it, a ball or modular sphere to it. So we need to prove this is true. And this one, locally, that means if B minus A is 1, then this is well known, is a local result. But whenever B minus A is bigger than 1, this is not trivial at all. And in general, may not be true, but for our case, it is true. So we use the standard, not quite standard, the energy functional. This is a standard energy functional. We take the square root in order to get a certain additivity. And then this is well known. And we suppose there's only one. Then all the critical values of the energy functional is given by the kappa m, which is the energy of the C to the m. And we define this one, the Morse index divided by of the C to the m divided by m. We know this limit always exists. And we call this the mean index. And since there's only one curve, therefore this must be positive in order to cover the whole global homology. And then the Morse and the Beatty numbers was computed by the Rademacher. Also, certain number there also computed by myself and my student. So this is well known in some sense. Now this is one of the most important ingredient in the proof. We are able to show that the Morse index, we can choose the Morse index satisfies this, we call that quasi-periodicity. So we can choose M0. Where to choose M0, I shall tell you a little bit about it in the next diagram. So we choose M0 so that the Morse index should be big enough. And then from there, we can choose this tau so that this is true for every m in between 1 and M0. So this is always added by this constant. And also the nullity are the same. That's very important. And then we also have a boundedness estimate. That means whenever this m is in between 1 and tau minus 1, this is bounded by a constant here. And then by these two conditions, these two results, let me see. And the other, let me say, okay, we go this one first. By those two conditions, we are able to prove this identity. I shall tell you later how to prove it. Suppose we have this identity, then depends on the case whether this D is odd or even. For example, is the top one. If the D bigger than or equal to 2 is odd, then this number is positive, the BD1. Then we can put this divided both sides by the BD1, and this side becomes the number here. This, we know this is always being even, we can prove. And then we computed this out. Then we found this one actually come out to be this number minus this number. Therefore, we got a contradiction. And we know this cannot happen. If the D is even, it is more complicated. Then this is negative. We also can divide it to the other side. We get a negative sign here and change the inequality. And we also compute this out, the total number sum of the Beatty numbers. We get a contradiction. Therefore, what is left is to prove this identity. So that is identity we climbed. The way to prove it is that we use the following diagram. Let me see. The diagram here, the horizontal one, is a dimension. We'll consider the dimension of local groups. The critical group, the zero-dimensional one until the dimension D minus 3, dimension D minus 2, and so on. And the sigma is the I of the C to the tau, and mu is the PC, that's the constant, plus D minus 3, and so on. We consider this horizontal line. The vertical line is the energy level. And we consider up to here. See, sigma plus nu plus 1. The top red line is the level just above kappa tau, below kappa tau plus 1. And we're going to compute all the alternating sums of everything in this rectangle. The reason Morse inequality does not apply is that which is too rough. Whenever you do this Morse inequality, you throw away a lot of information. Here we want to keep everything in consideration and compute all the alternating sums. And beyond this level, we know everything is 0. And also below this one, by our estimate, we know this one. The bounded estimate gives us all the 0 here without this 0. This 0 is given by a theorem of Kingston in 1993. So that means we have enough zeros. And also, everything above this red line, the kappa M0, this is 0 by our choice of the M0. So that whenever you go to the iteration of the M0, the Morse index already been big enough, already go to the right-hand side of this time. Therefore, everything above should be 0. Now, in order to prove our theorem, we consider from here to do the alternating sums. Since we have a 0 here, we can go through line by line using the exact sequences. So we denote this one by the whole alternating sum of the rectangle. I already told you the rectangle. Then this can be given by the kappa tau, below kappa tau modulo 0, plus the alternating sum of these Betti numbers minus the whole thing on the top, modulo the kappa tau. That means we consider here everything on the top and below this one. Consider the whole space and this one, and also between these two, these three the triples. And then this is the Betti number. This one we do not know, but we just denoted by kappa. Since we have only one unknown thing is controllable. Then the question is, we need to understand this one. This one means that everything on the top modulo this one, modulo this line, modulo everything below this line. So still there is something which is non-zero there. And we climb the whole thing modulo the top this one coincide with the whole thing modulo 0. Therefore, that is the Betti number. So we climb this one. We climb this one actually is the Betti number. The reason is that since if we are able to prove the top part modulo this part isomorphic to top part modulo this part, then they should be equal using the exact sequence. I don't know how much. So firstly, locally, we know this is true. Locally means that whenever b minus a is 1, so everything on the bottom can be shrinked up. For example, suppose I have never set here and never set here. This is a point here. Then since there's nothing, no critical point in between, therefore everything can be shrunk up. Therefore, everything becomes local. Whenever local one is isomorphic, we know everything is true. If this one go to here, the local one is isomorphic to each other, then this part modulo this one and this part modulo this one should be the same. But whenever it jump to the energy level, it's non-trivial. So firstly, we can go through the diagram, one by one. And the diagram tells us, actually there are some periodicity in the diagram. That means we already chosen this tau. This tau actually is a multiple of the n. What is n? N is we call that analytical period of the homological groups. So no matter what is the path we choose, we show that all these the alternating sum of the homological groups actually is periodic, and the period is tau, is n. So whenever we pass through an n, then the whole alternating sum of these two lines will be the same of the top of these two, and also will be the same as another two, and so on. So there is such a number. So that means the total sum can be written as the from 0 to kappa tau, can be written as the from 0 to kappa n. N is much smaller than the tau. Then we get tau over n this much times the sum here. So we get this number. Then this part by the theorem of the, then this part actually we call this, we give it a name. That is we call that average is the Euler number of this whole thing. Then by Rademacher theorem, proved by 1992, we know this number divided by n should precisely be the minimum index times the b of times d, b of the d1. So this is Rademacher identity. Then by the result of myself and my student, we showed this number equal to the sum of these two whenever this the mean index is rational. When it's irrational, this is not true. But since we have only one closed curve, this number have to be rational. Then use this result, we just get the identity there. So the original one is the whole thing modulo the lambda to kappa tau. So we consider the triple of this one and this one. Then using this triple, we get these two are isomorphic to each other. Using this triple, we know these two are isomorphic to each other. So if we are able to prove these two are isomorphic to each other, then we are done. So what left is to prove actually these two, really globally, they are the same. No matter how big is the kappa m0, no matter how big is it. The idea is that we want to prove this one modulo this one, actually isomorphic to this one modulo this one. Okay. So the theorem is this one, and we want to use the condition we did here. Intuitively, it comes out since the index, the nullity part are the same. So actually the local group essentially is determined by the nullity part. Therefore, the whole thing should be, since we already chosen this tau to be a multiple of the.
Yeah, we say that this kind of if the theorem, but this assuming there is only one geodesic, right?
Yeah.
Means it has no application.
Hands-on application.
So to contradiction.
We want to get a contradiction.
So it's theorem which applies to empty set.
Yeah, sure.
No. We suppose there's one. Since the
At least one.
at least one.
At least one, not exactly one.
At least one.
At least one.
Oh no, yeah. No, sorry, it should be exactly one. Exactly one.
It was empty statement. Theorem is empty.
Yeah, no,
No, it's proved that there's one.
proven contradiction.
Well, you use it, but as a theorem to say, if some satisfied, which is never satisfied, then everything is so. As a conclusion of this, any statement can stay corollary of this.
No, suppose.
Suppose there is only one.
It's kind of stairs.
Yeah, we want to get a contradiction. Okay. Yeah, you certainly you are right. But then later on we shall do when we have more than one. Later on. Okay. So from this formula, we know that actually the homology actually comes from that this gives us one more sphere, one more ball modulo the corresponding sphere. So intuitively, this should be true. And the idea is that, for example, this is a very simple example. We consider a function here, which is defined on the interval from y1 to y2, and has the level set look like the curve on the bar. Suppose we have the Morse index at each point going out by the same additional the adjustment. That means we add one dimension at each critical point. Then we get a whole two-dimensional thing. But this two-dimensional thing has the same homology with the original one. That is the idea. And this one shows that if the Morse index does not satisfy the condition, for example, here we add one dimension here we add nothing, then the theorem is not true. This is not, this side becomes 0. This side, so this is a necessary condition. Later on we show this is also sufficient. The idea is that we consider induction argument using the Phi lemma. So we consider the B and the kappa B and modulo kappa A. So at the very beginning, we suppose B minus A to be 1. So this part should be true. The whole thing actually, whenever B minus 1 is A, everything is true. So here, B minus 1 is A, we can construct this out. So for next step, we consider B minus A is 2. Is 2, then what left actually is we can construct this out, this map. This map essentially depends on the iteration map. Since the iteration map goes from kernel to kernel. What is important is in the proof is the commutativity of this diagram, and also this one. But these two are coincide. Therefore, we need to prove this one. This one actually will take 3 years to understand it. So that is what we want to prove. The idea is the following. Actually, this is induced by the iteration map. This is the boundary. And the idea is that we consider this case. So we suppose the B minus A is 2, and we consider, maybe we may go back. We want to embed this one, embed the manifold here into the bigger manifold. Since everywhere we add the same dimension. And we need to show this is possible. Also, this one is possible. The reason, let me see, I probably didn't show that on the diagram, on the PPT. And the way is that we use the property of the energy functional. We take the square root of the usual energy functional so that it is additive. The additive things means that suppose we have let me see if I have a picture here. No. Suppose we have let's see. A generator look like this. Then we can push it to embed it to the higher dimensional case. And we can add we call that the mat to it, so that we can choose this tau very carefully and prove this also can be mapped to this part. This is a higher dimensional one. And we prove if there is a path, actually defined by the negative gradient flow. From here, go to another critical point. This is the C to the M, C to the, for example, B. This is C to the A. Then here is the C to the tau plus B and C to the tau plus A. There should also be a path precisely go the same way to there. We need to prove this. Then once we can prove that, then since everywhere we add the same dimension, then we can go through to get it. But this part is not easy to prove. So by that proof, we can go through this one. So essentially, we do the induction argument for the B minus A to be 1. Then they do the commutativity part. That is this proof. Then for the general case, we also can do it. Then do the induction argument for every B minus A up to M0. Essentially, that is the proof, but there involves a lot of the details. And for the next step, we are considering these two. Firstly, the two case for the S2. And this was written down when I gave a lecture in the UBC in the beginning of July. And the last two consider higher dimension, last three consider the higher dimensional case. Now I think that we already.
Reversible meaning symmetric, or meaning reversible method, symmetric.
Yeah, if it's symmetric, there should be infinite many.
This reversible means symmetric.
The metric?
Reversible, reversible.
Yeah. Reversible means symmetric for the Fencer case. Now I think we already go through all the critical point of the proof of this one. So for the Bungart and Frank's theorem, we can give a new proof. And also for that case, that is proved by the Hofer, Zinder, and Wysocki under two conditions. Using our method, we also, since we have not only been able to dealing with the one curve, we are able to dealing with whenever it's finite many. So for both the two, we need time to write down everything. But now all the difficulty part already passed. So I believe everything is okay. So I didn't claim we already proved, but it's very promising, I think. So actually we use the identity. The identity also holds for the whenever, for example, for S2. For S2, we can classify the closed geodesic into two parts, rational one and irrational one. Irrational one means that since it's S2, so the linear Planck map is a 2x2 matrix. So the 2x2 matrix is a rotation matrix, which is cosine theta, negative sine theta, and the cosine theta. And also if the theta over pi is irrational, then we call this is a irrational case. Then all the other closed geodesics with the Planck map does not conjugate to this case, called rational. Then first, using our method, we can prove there cannot be any rational closed curves. Then second step, we prove that actually in 2008, with one of my former students, we already proved another one. Whenever total number is finite on S2, there should be always at least two irrational closed geodesic, which essentially describes the result of the cutoff. Then whenever we have more than three, at least three irrational closed geodesic, we are able to show there is a contradiction. Therefore, there should be always two. But this means that whenever we consider the closed geodesic, which is homologically visible, that means whenever it's a local group, somewhere is non-zero, then by the periodicity, we know there are infinite many possibility, which is non-zero. Then the last step, so for this one, whenever we know homologically visible one is infinite many, that is already good enough. But for the top one, we need to show there is no the invisible one. For invisible one, we're now working on that. Invisible one has three cases, since it's 2x2. All the eigenvalue both are 1. And we are able to show, we found a way. That means if we have an invisible one, we can construct a new one, which is visible and which is not the original two, which has to be something else. But we already, for the visible one, we already showed there should be either two or infinite many. So we get a contradiction. Therefore, we should have at least precisely two or infinite many. But still, for these two, I believe just time to write down. But for the higher dimensional case, since this highly depends on the estimate, whether the estimate can go through or not, therefore need time to adjust every step, whether it can go through or not. The situation is much more complicated. For the S2, it's very simple. All the iteration formula and the Planck map are very simple. Okay, thank you very much for your attention.
Are there any questions?
At some point in the lecture, you pointed out that the number of closed geodesics should be an interval, integer between PD and QD infinity. What is the meaning of these numbers?
Actually, we believe, for example, for the sphere, I believe the two numbers coincide with the number of the cutoff. But for the other manifolds, which is not sphere, maybe we got an interval. We do not know. And also, if one consider beyond the simply connected case, which may be much more complicated. Our proof is based upon the result of the Sullivan. Yeah.
I remember many years ago, my friend Raoul Bott, who worked on these things, told me that some of the early work on closed geodesics, which used Morse theory, was incorrect because it didn't take account of the symmetry. And that for that purpose, you have to use equivariant cohomology.
We do use that. We do use that.
Mention it, but that's for I guess for the, and then of course you have to work with mod 2 cohomology. I mean, you work with symmetry group mod 2. Many numbers have to be defined.
Raoul Bott actually he developed the 13th iteration formula, the first one, published in 1956, and which just reduce the computation of the mth iteration of the Morse index. Morse index of the mth iteration to this one. He computes the c to the m, which should be the sigma, the omega to the m should be 1. So all the m's the unit root of the 1, and then the Morse index of the omega index of the path, for example, C to the n. And frankly speaking, this is a very beautiful result. The first result is theoretically useful, but they give no much information. This is not computable. So we need a precise iteration formula. The formula is here. So we need to do a kind of the normal decomposition. This normal decomposition keeps all the iterations have the same Morse index. Then this gives us a precise formula according to the normal form decomposition. So use this formula, we can derive everything. This was published in 2000 in Advances.
Are there other questions? We thank Professor Yiming Long.
Thank you very much.